Hello dear students, good morning. This is Mr. Shinde, working as an R&D engineer in ABB India Limited, Nashik. To give a little introduction about me, I have completed my Masters of Technology in CAD/CAM CAE discipline from RIT, Raja Rambapur Institute of Technology, Islampur, Sangli. I did my BE in Mechanical Engineering from Sandeep Foundation, Nashik. And then for last 2 years, I was working with CG Power and Industrial Solutions Limited, Nashik. But recently I've switched over to a new organization called as ABB India Limited as an R&D engineer. So before we begin with this presentation, I would like to thank Professor Chetan Zada for putting up this session on metal burnishing process. Well, I'm not so much involved into this process or its applications for recent years, but it's just an overview to make you people understand what this process is all about and where it is being used in industries, how it is useful, what are its drawbacks and all those things. So we will see a detailed agenda for the today's session in upcoming slides. So before we proceed with this today's session, let me just ask you people some question. Let us go through the next slide. Yes, so as you can see here, there are three terms noted down over there on the top of the slide: science, engineering, and technology. So the question to you here is, what do you understand by these three terms, and what is the difference between these three terms? So you can put up your answers, you can put up your views on the differences in these three terms into the chat box. And just let's make this slide interactive a little bit so that we can have your views on your views on these three terms and how do you perceive the differences between them. Yeah, so please go ahead, those who can answer about this. Okay, I can see some of the answers coming up. Some say okay. All right, very good. Thank you for this good response. So I'll just put up all of your answers in simple small phrases, small words. So most of you people are saying that science is something which is nature's law. Science is basics of everything. Science is physics, chemistry, mathematics, biology. Okay, good. So good. That's very good. Engineering is something that people are saying that engineering is about building up machines. Okay, building up constructions, infrastructures. Okay. Engineering is bringing up energy. Okay. And technology. Okay, that's what I wanted to know. So yes, most of you have said that technology is about designing something better, or going into the research field. So that's a very vague definition of technology what you people have said, but here I would like to clarify this technology term into a little bit details of it. So okay, that's it. Very good. Thank you for the response. Let us hear it from my side now for the differences between science, engineering, and technology. So it is not that I have had these thoughts into my mind. It is basically the differences that I have understood or that I could hear from one of my previous managers. So I'll just try to dictate his views on what are the differences between these three terms. So let us begin with science first. So what is science? As you can see here in those two images, science is something which is basics of everything. Yes, as some of you rightly said, it is nature's law. It is science is everything which is there into existence in nature for a long time, which is unchallengeable, which is unchangeable, and something which is there. Just it is there. So just to give you an example, ओके भैया, सेफ को अगर नीचे गिरना है पेड़ से तो वो नीचे गिरेगा ही, क्योंकि देयर एग्जिस्ट्स a gravitational force which is pulling it downwards. So that's how the Newton discovered law of gravity. Atoms has neutrons, protons, electrons into it, nucleus and all those things, orbites, electrons are moving around the nucleus around in the orbites, so which is bound to be there, which we cannot challenge. अभी किसी को जाके पूछ नहीं सकते भैया दिखाओ एटम में न्यूट्रॉन कहाँ पे घूम रहा है, कितने ऑर्बिट पे घूम रहा है, किस डायरेक्शन में घूम रहा है. We cannot just ask it, isn't it? But it is there into existence and we believe that it is there and we apply those things, isn't it? Acid और alkaline mix करने के बाद में we are supposed to get a neutral solution. वाटर का pH 7 होता है. ये हो गया फिजिक्स केमिस्ट्री के बारे में. To talk about biology, I would give an example of photosynthesis process of trees. So trees make use of sunlight and they do their energy synthesis by giving some byproducts which are useful to the nature earth. They produce oxygen as a byproduct, so which we inhale for ourselves. And so likewise they have also xylems and phyllems into them for their water absorption system, capillary system. So that's something which is there into nature for a longer time, and which we cannot change, which we cannot challenge. But yes, it is there. It is believed that it is there. Now then, what is engineering? Now since we have some basic principles with us, how do we make use of them to have a better lifestyle, isn't it? I've put forth some images since you people belong to the mechanical engineering background, but yes, you would also agree that it is not just about mechanical that engineering talks about. Yes, even though mechanical is one of the oldest branch of engineering, but then again there are other aspects of engineering also, isn't it? So we made use of those basics of chemical elements and we tried to form some medicines which are useful for people. We developed computers, we developed mobile phones, pagers, landlines and whatnot. So that's what we did. We made use of the things that are present there in nature and we developed something that is useful for the people of this earth. So isn't it? So यहाँ पहले चक्कियाँ घूमती थी लकड़ी की, isn't it? तो लकड़ी की चक्कियों पे कुछ एकदम ओल्डेस्ट डिज़ाइन था, तो उसको हमने थोड़ा सा इम्प्रोवाइज करके कुछ किया, तो उसको इंजीनियरिंग में लाया. तो उस चक्की का यूज़ हमने कुछ मशीन्स में किया, रोटरी मोशंस पिक्चर में आई, लॉज ऑफ एनर्जी है, basics of forces, energies, equilibrium, all those things are there which we are bringing into application as a part of engineering, isn't it? So then what is technology? This is where many people get confused about, in like more or less in just two aspects of it. Like some people take technology as a subsidiary of engineering, or they don't see any difference in engineering and technology. On the other side, many people believe that technology is all about design, bringing up something new into market, sort of research and developmental activity. But that's not the only aspect of technology. Let me clarify this thing to you here. See, bringing up something into market or developing something new, for this you don't need technology. For this you need to have some basics. You need to have that approach to bring it into market, which is basically an engineering approach. It's not a technology approach. But then what is technology? Technology is something that you develop it in such a way, you modify your existing engineered product in such a way that it can be used by masses, it can be used by people, it can be used by communities in all. So to give you an example here, भैया computers earlier ज़माने में हुआ करते थे, isn't it? उनका size क्या था? Remember the first computer developed by some scientist, I don't remember the name now. So remember the first ever computer. It was of a room size. Now each house has at least one laptop, at least one workstation, at least one desktop in their house. So what has happened? Computer to pehle bhi tha. It was already there. It was developed. It was engineered by applying some basic science principles. But then why these laptops and workstations and desktops came? Because everybody cannot just go and sit in front of the biggest computer and work there. So it was a need of time that each house, each individual carries his own computer, and that's where the technology came into picture. Again, mobile phones. Remember the days we had those dial-in options, dial-in phones like or STD phones or ISD phones, pagers, walkie-talkies, everything into their usage. They were working fine, and they were all engineered products. But then today, if you see, a compact sized, very slim trim mobile phones have been developed, which you can carry in your pocket easily, anywhere, anytime. You can talk to somebody, you can surf anything onto them, you can do a lot of with it. So that's what technology is. So now in this process, it's not the only designers that are involved. It's basically the marketing guys, the designers, the research and development guys, the supply chain guys, the production people, the sales people, services people, all are involved into it. Because see, if marketing guys do not work hard to survey the market trends, to survey the needs of people, they won't be coming up with some new requirements. So if marketing guy doesn't give some requirements, technology people or design people will not be working on anything new, because they might not know what future is going to demand from them. Likewise, if they don't design something new, productions or supply chains would not work in order to have a better, efficient, mass productive system into their presence, isn't it? Same way, sales will not be having a good enthusiastic job, because if same product is to be sold multiple times to multiple customers, it will be some sort of boredom to them, isn't it? But the technological improvements are bringing in enthusiasm, bringing in keen interests for each and every individual, each and every stakeholder involved into the process, right from conceptualization till the end of the product life cycle of the product. Now furthermore, this is something a conventional or traditional technology explanation that I've given to you, but nowadays, looking at the today's era, what we see technology as is, there are different terms to it. Digitalization is there, then artificial intelligence is there, AI, then IoT is there, in the Internet of Things, then Industry 4.0, artificial neural networks, digitalization, globalization. All these are technological advancements that are coming into picture nowadays, which are bound to happen in future in almost every product chain, every product group, every work sector. These are the things which are in demand nowadays. These are the technologies which are going to come up with quality products for usage to many people at a single time. Cloud computing even. You can sit at some location and you can share the files. You can work online on cloud with multiple platforms, with multiple stakeholders involved into it, giving simultaneous inputs and producing a continuous constant single output. So that's something which is coming up as a technology in future. All right. So I have a lot to say about this slice, but I'll not continue. I'll stop here about this because the main focus is on burnishing process. So without wasting much time, let's go to the next slide. We'll quickly go through the agenda. What we will be discussing about burnishing today is, first we will go through the introductory part of it. Then we will see some mechanics behind it. Then we will see what are its effects on mechanical components, how it is being used in manufacturing industries, what is its classification, what are its benefits, what are the drawbacks, then where it is being used as a process, and some miscellaneous, like we will go through some videos, we will see uh, some other parts of it. Okay. All right. So let's quickly jump over to the introduction of metal burnishing. We will see some definitions and some basics of burnishing, what it is exactly. So before we begin with the introduction, let me clear that, or let me put forth it to you that why burnishing has come up as a manufacturing process. Why? I mean, since it is a super finishing process, we also have some other super finishing processes like honing, lapping, grinding. Then why burnishing came up as a process? Okay. All right. So these recent technological developments, what we have seen so far, are like demanding sort of good quality, superior quality products which can serve the customers for a longer lifespan. So that's the basic demand for any product in future which you can dictate about it. So the engineers have to come up with a good sort of products with better qualities, like but also without compromising the production cost, because then if you offer something at a higher quality under the name of good quality, customer may not be able to accept that product because he will have to pay more for this. But then again, customer demands something good with a reasonably fair quality cost. So the engineers have to work a lot on this, and they had to develop processes that will like serve the needs of the customers in the market, isn't it? So these expectations are served. That was the main focus of engineers, isn't it? So the service behavior and life of the component depends mostly on the surface properties, and this is the reason which is why significant attention was spread on post-machining operations, because the conventional machining processes like turning, milling, etc. do produce surfaces with inherent irregularities. So the products or workpieces produced by the traditional methods of turning and milling do have surface irregularities or imperfections present on it. And that's where the need for surface finishing operation that will nullify these irregularities or clear off these irregularities, and also improve some other parameters or other properties of surfaces like surface hardness, corrosion resistance, wear resistance, fatigue properties. The focus was there on that. There was a need for this operations. So these properties can be increased by utilizing surface plastic deformation processes, which normally do not remove material but improve the surface properties by deforming the surface plastically. Yes, obviously under some compressive loads. So under this external load, the surface of the component is subjected to basically a cold working. And one such surface plastic deformation process, SPD process, is burnishing process, which is widely accepted by industries nowadays. Okay. So that is what I was about to go over. So burnishing, that's where like burnishing has come up into the manufacturing sector as a process. So to put it in front of you in simple words, as a definition, burnishing is simply a process of surface finishing for the workpiece or for the part or for component by plastic deformation due to sliding contact with the another object. Okay, so that's the basic terminology that I would use for burnishing as a definition in simple words. So burnishing is a surface modification process which basically produces a very smooth surface finish by the planetary rotation of a tool over a turned surface or a machined surface. Now this tool may consist of one or more balls or rollers depending on which type of burnishing you're doing. This process, as I said earlier also, that basically does not involve the removal of material from the workpiece. And as I stated earlier also, that the conventional machining processes of turning, milling, etc. do have surface irregularities present on their surfaces. And what do these irregularities consist of is basically peaks and valleys of the surface part. So the peaks and valleys which constitute the surface irregularities are there. Now the force applied by the burnishing tool will force the material from the peaks to flow into the valleys. This will reduce the height of peaks and depth of valleys. That's the simple funda. Thereby this will reduce the surface roughness and hence we term it as a surface finishing process. Now since there is no heating of the workpiece involved, there is no preheating involved, this is basically a cold working process, isn't it? Now yes, due to this burnishing technique, compressive stresses are developed onto the surfaces. Then the question may come that yes, there are some other compressive stress development processes like shot pinning or laser shot pinning. Then why do we need burnishing? So yes, there are processes like shot pinning or laser shot pinning which do develop compressive stresses onto the surfaces, but these stresses were found to be relaxed when the part or component is subjected to heat. So this thermal relaxation of the compressive stresses developed by shot pinning techniques will reduce the component life and reduce its performance. That's why burnishing came up as a process that could impart thermally stable compressive stress on the surface. Now since we call it as a thermally stable, it is basically without heating of the workpieces or without preheating of the workpiece material or raw material, and that's why it is termed as cold working process. Okay, I hope you understand this now. The basic principle is like okay, the contact stress. Alright, let me go into a little detail of it. Burnishing process is considered as a cold working process because the surface of the workpiece is like subjected to severe stress due to planetary rotation of the workpieces, as I mentioned earlier also, planetary motion between the tool and the workpiece and the pressure applied by the tool. So when this stress exceeds the yield strength of the material, it results into the plastic flow of the material from peaks of the surface irregularities into the valleys, thereby reduces the surface roughness. This also induces thermally stable and long-lasting compressive residual stresses. Now this burnishing can be both intentional and unintentional. When it occurs as unintentional, it is basically treated as a failure mode. But when it occurs as intentional, it is basically a controlled process, controlled manufacturing process rather. So as I have mentioned earlier, let me just put on my pointer. Yes, if you can see here in this image, the bottom image, there is a workpiece, there is a ball which is hardened ball or roller for that matter, you can say, with some radius r. Now both of these, like tool and workpiece, both are rotating. Understand this, both are rotating. That is how the planetary motion is being taken out from here, and there is a constant feed. So this process involves pressing of this hardened ball or rolls into the workpiece, giving a constant feed motion to the same. Now this will develop compressive residual stresses on the surface of the workpiece, and hence this will improve the fatigue strength and wear resistance of the surface. That's the basic of metal burnishing process. Okay, let us go to the next slide. Now, since we we know the basics of what exactly the metal burnishing process is all about, let us see the basics or basic mechanics behind it. Okay, so let us illustrate this mechanics by considering the action of a hardened ball against a softer flat surface, workpiece or plate. Now just imagine a case if the ball is pushed directly into the plate. Now where is ball, where is plate? You'll be get confused. Then what is this water all about? So let us, I have purposefully taken out this image for you people. Like imagine this droplet as a hardened ball, steel ball maybe. And imagine this water surface as a flat workpiece top surface. Okay, now okay, so if the ball is pushed directly into the plate, stresses are developed on the contact area of both the parts, like both the objects, steel ball also and the softer workpiece surface also. Now as this normal force increases, okay, both the ball and the plate surface, will deform. Now this deformation caused by the hardened ball increases with the magnitude of the force pressing it, isn't it? The deformation caused on both the object surfaces will increase with the increase in magnitude of the force with which we are pressing this ball into the workpiece. Now, if the force on this ball is small, okay, and once we release this force, both the deformed surfaces of both objects will regain their original shape as dictated over here. This normal force is applied on the ball, which will cause some sort of indentation onto the workpiece surface. But if this force is too small and when it is removed, the surface will regain its original shape. Okay. Now, in this case, the stresses in the plate are less than the yield strength of the plate material, and that is why the deformation is elastic. That is the reason why the material or the surfaces are regaining their original shape. Now since it was said earlier that the plate is of a softer material and the ball is of a hardened material, the plate's surface will always deform more. Agree? Now imagine a case when a larger force is used on this hardened ball. If a higher force is used on this hardened ball and it is in a normal direction, then an indentation which will be caused onto the workpiece surface, isn't it? And this indentation will be surrounded by a ring-like formation of the flown material. Now, due to pressing, the material will flow where it will flow, the outside of that indentation, and this flow of material will cause a ring-like structure to appear. Got it? Which is basically a displaced material by the pressing action. Now this will happen only when the plastic deformation is allowed to happen, meaning the force is high enough to exceed the yield strength of this workpiece material. Then only in that case only this indentation with the outer ring like structure will be seen. Now imagine another situation. Let us take up a case that same workpiece, same ball is taken for the experimentation, but now in this case the ball will not just be pushed down, but it will also be dragged, maybe along the workpiece or across the workpiece, it depends. But the direction won't matter as such over here, in the sense that whether it is across or along, that won't matter. In the case of dragging of the ball along the workpiece or across the workpiece, the force will be resolved into two components. One will be normal to the workpiece and another would be tangential to the workpiece surface, isn't it? Now here, if the tangential force is high enough, or the tangential component of the force is high, then ball will start sliding along the plate, isn't it? And at the same, before we take up the cases, since the force will be resolved into two components, tangential and normal, the tangential force will try to drag the ball along the workpiece, and at the same time the normal force will try to cause some sort of indentation or a mark or deformation of the surface, just as the case which we have seen in the static situation. Now there could be cases like if the normal force is low, okay, if the normal force is low, the ball will simply rub along the workpiece, but it will not cause any sort of deformation since the normal pressing force is less in magnitude. Got it? So are you getting it? In the case where the tangential force is higher than the normal force, the ball will drag along without giving you an indentation mark onto it, because the normal force, the pressing force, is less in magnitude, so it will just glide along the workpiece, to put it in simple words. Now in another case where the normal force is high but tangential force is low, the reverse case. Now in this case, this higher normal force will flow the material along the tangential direction, and simultaneously it will cause, or this flowing of material will cause a formation of trough, isn't it? Are you getting my point? Just see there in this case. Now this is a plastic deformation occurring. So as I'm gliding the ball along this direction perpendicular to this workpiece, I mean towards our eyes, this sort of cup or curved formation will be there, which is basically flowing of material. Now imagine that this workpiece comes along in a length in the direction perpendicular to the screen, so this indentation will be along the direction perpendicular to the screen. So that is basically the burnishing process. Okay. So that's all about the basics or basic mechanism of burnishing process. So what has happened here is a material has been flown from the highest points to the lowest points, like peaks to valleys. Now this burnishing can also occur in between two flat presses, a flat surfaces which are into contact for a longer time with irregularities or asperities present in them. So what will happen over a period of time is, when some compressive forces are acting on the flat surfaces, or maybe some impact forces are acting on the surfaces, eventually at some point in time there will be a deformation of those asperities or irregularities present on both the surfaces, and it will cause a formation of a smear texture, a smooth texture on the plate surfaces. Okay, so I hope I'm clear with the mechanics part of this metal burnishing process. So let's move on to the further part of it. What are the effects of metal burnishing process on mechanical components? Now, metal burnishing is not always desirable because it can have several unpredictable effects onto the mechanical components which are there into operation, isn't it? So to say, or even a light sort of burnishing will significantly alter the surface finish of the part, and initially this finish will be smoother, but with the repetitive sliding action, some sort of grooves will develop onto the surface along the sliding direction. The plastic deformation associated with burnishing will harden the surface and generate compressive residual stresses. Now, yes, this will create a conflict in your mind that earlier I have said that burnishing creates a surface hardness or compressive residual stresses development. So it should not be a problem, isn't it? Yes, it should not be a problem, but up to certain limit. If excessive burnishing happens, this will lead to spalling. Now, what is spalling? Spalling is basically, subsurface crack development, and then this phenomenon of crack development or crack initiation below the top surface of the workpiece will eventually, over a period of time, cause the upper layer of the surface to flake off. Are you getting my point? Now, again, burnishing may not always be good in the sense that it might affect the performance of machine. The plastic deformations associated with the burnishing can create a greater heat and friction between the sliding parts, and then this will reduce the efficiency of the machine itself, and it will also limit the speed since there is a friction involved into it coming into picture during its operation. So again, this burnishing plastic deformation may alter the form and geometry of the workpiece or of the component, which will reduce the precision and accuracy of the machine. It might not perform the function that it is intended to perform over its period of operation. So again, as we all know, the combination of high friction and degraded form is always a bad combination, isn't it? To put it in simple words, imagine a surface with friction, high friction, causing heat generation, and also the part is not having the geometry or form as it is supposed to have. In that case, both are worsening factors, like friction is worsening factor and a bad form or undesired form is also a worsening factor. So two worsening factors when come into picture, they will surely make the component to fail into its operation. So that's how basically burnishing is unintentional when it is, occurring as an unintentional phenomenon. Now, how do we avoid this unintentional burnishing? Can we eliminate this? Surely we cannot eliminate this, but yes, we can avoid it to some extent. Now, how do we avoid it? Now, the places, most of us or almost all of us have seen some or the other sort of machinery around us, which has a certain movements of the components involved into it. Multiple types of movements of the components present into some machine or some assembly. So we have seen this, we have observed this at multiple places. Now, While designing itself, can it be thought of in this sense that can I avoid this sliding action? Can I avoid this rubbing action of between two components? Can I have some alternate option to the sliding action in the sense that maybe can I put some rolling action between them? Is it possible that the components will give me a same sort of performance, not exactly the same, but almost nearer to the expectation sort of performance to me by making use of roller action instead of sliding action? This thought should be given while designing. Uh, if it cannot be avoided at all, the sliding action cannot be avoided at all because the function of that particular assembly or subassembly demands it, then can we make use of some sort of lubrication between the two mating components? Moreover, if it is already there, if it is already specified by designer that some sort of lubrication is to be used during its operation, but still I'm getting some sort of failure into it, then can I make use of some other alternate lubricant which will reduce the friction basically? So that's how we can avoid this natural unintentional burnishing from occurring into the operational life of the product. Got it? Let's move on to the intentional burnishing. So intentional burnishing. Now since everything has two aspects, one is good, one is bad, unlike burnishing also has some good aspects of it. It is not always bad, but only when it occurs in a controlled manner. So when burnishing occurs in a controlled manner, it can give you a lot of benefits. Burnishing processes are used in manufacturing to improve the size, shape, and surface finish of the or surface hardness of the workpieces. It is basically a forming operation on a smaller scale. To put it into simple words, the benefits of burnishing often include, like delaying the fatigue failure, preventing corrosion, elimination of visual defects, closing porosity defects, creating surface compressive residual stresses. These are all benefits that we get when burnishing is applied or burnishing is carried out in a controlled manner. Now this burnishing has several forms like roller burnishing or ball burnishing depending on what type of burnishing you're using. Again, the workpiece can be at a higher temperature or at a room temperature. When it is at a higher temperature, the purpose is basically to reduce the wear of the workpiece tool, wear of the tool, to have a longer lifespan of the tool. Why we need to have a longer lifespan of the tool, that we will see into the advantages or disadvantages of burnishing. Now this burnishing also occurs in your conventional machining processes like turning, milling. In case of turning and milling, when the tool is used for multiple times and when the tip of the tool becomes blunt and you're using it into the operation of turning or milling, it is basically causing a burnishing operation. Or on the contrary, if you're using the tool with the small cutting depths, then also the operation is similar to burnishing operation. If the workpiece material itself is gummy, like epoxy, like nylon, then the operation that you carry out, cutting operation, turning or milling operation basically that you carry out, is can be resembled to the burnishing operation. The only thing is that some parameters need to be controlled. Then only you can resemble it to burnishing process. Otherwise it will be a normal turning or milling operation. In case of grinding, as you know, grinding wheel has randomly oriented grains into it. So these grains will be sharp at some point in time and blunt at some point in time. So grinding, isn't it? So grinding will also serve as a burnishing process. or there is always some amount of burnishing occurring there in the grinding process. So this is okay. Now let us see. Yeah, the last point, that this metal burnishing, when carried out in a controlled manner, can be used as a deburring operation also. So that is also one of the benefits that we can take out of it. So it is especially useful for the removal of burr in the, you know, through holes that are drilled into the workpiece. Through holes, when I say through holes, it has openings from both the sides, top and bottom, because in deburring operation, the burnishing tool will be passed from one end and it will be taken out from the other end. That's how the deburring will occur. Okay, so that is about intentional burnishing. Any doubts up till now? Okay, so now let's quickly move on to the classification of burnishing. It's already 45 minutes. I'm taking a lot of time, but let us see what are the classifications of burnishing process. So burnishing process has two types: ball burnishing and roller burnishing, with some minor change into both. So in ball burnishing, the tool basically consists of one or more spherical balls. Now these balls are held in a shank of the tool holder by means of some hydraulic pressure or spring force, and also the corresponding reactive force from the workpiece that acts on the balls. Now this tool is fed along the workpiece. When it is coming into the contact with the workpiece surface, the burnishing process will occur. Now the amount of burnishing will depend on the burnishing force. Burnishing force will depend on the hydraulic pressure or the spring force that is given onto the ball. So the image here shows a typical view of a ball burnishing process, or a schematic of a ball burnishing process. This is a typical ball burnishing tool, and these are a little bit of advanced ball burnishing tools that are into practical use. Now this variation of the hydraulic pressure, as you can see in the schematic, there is some sort of hydraulic fluid present into the tool holder. This is the spherical ball, which is also circulated or surrounded by the hydraulic fluid, and there you have a tool holder or shank, and the gray part is a workpiece, and likewise the tool will be fed. So whatever irregularities are there present on the surface of the workpiece will be flown out, and a smooth finish can be obtained. Now in some cases, oversized balls can be used to push them to maintain the hole diameters, like just similar to the deburring operation that we have just talked now about. Also, there is one more variant of ball burnishing called as vibratory ball burnishing, wherein the ball burnishing is carried out with some sort of vibration motion assistance. We will see this into the last slide of this presentation. What is vibratory ball burnishing? How it is used with some practical example. Now talking about roller burnishing, it is similar to ball burnishing. The only difference is that instead of balls, rollers are used. Now these rollers can be single roller or multiple roller mounted on a shank of the tool. Shank can be connected to the machine tool post like lathe or milling machine. Now again, same way as unlike ball burnishing, when the tool is made in contact with the workpiece, the burnishing will occur due to planetary motion. So you know the basics of it now. Now these rollers can be tapered or they can also be of a form like during operation of burnishing they will take up the shape of the workpiece itself. Again, the hydraulic system components or shaft fillets or like sealing surfaces are the applications of this roller burnishing process. Using roller burnishing process, a close control of size can be achieved. Not just roller burnishing, but also ball burnishing process. So that's part of the advantage of this process. Okay. So moving on to the benefits of it. On accuracy part, a fine control of the size is possible by using this burnishing process, isn't it? Parts can be produced by burnishing with high control over the dimensions, and hence very close to tolerances can be achieved. Then moving on to the next, surface finish. A good surface finish or very smooth surface finish as high as 0.05 or 0.01 microns is possible to achieve with burnishing process. Then improved physical properties, as we have already discussed, burnishing produces hard surfaces, causing them to be fatigue failure prevention proof, wear resistance, corrosion resistant surfaces due to cold rolling operation or cold forming operation. And basically it is because of the compressive residual stresses that are induced into the surfaces of the workpiece. Burnishing is economical in a sense that the burnishing tool can be mounted on your conventional machining equipments like lathe machine tool post or milling machine tool post, like that. So you need not to remove the workpiece and then take it to some other special purpose machines, then mount the tool burnishing tool onto the tool post of that SPM, and then hold the job into the chuck and then carry out the machining. So in a way, since the conventional machines can be used just by changing the tool on the tool post, there is no need to adjust the workpiece. So this will basically reduce your cycle time and thereby giving you a saving in time and then the cost. So that's how it is economical. Adjustable settings. Burnishing tools can be developed so that they can be used for multiple purposes. Like a single tool can suffice the purpose of burnishing various complex surfaces. As I mentioned, varieties of tools can be used for processing. There is no chip formation in this process. It is less noisy process. So that's about the benefits or advantages of metal burnishing process. Moving on to drawbacks of this process, the high initial tool cost is involved into this process because burnishing tools in some cases can be customized ones based on the complexity of your job. But nevertheless, for the tool itself, a high initial cost is required because the tools are made of a special hardened materials like cemented carbides or tungsten carbide tools, diamond tools, hardened steel tools. So making up these tools with some sort of processes and good quality material will take up some initial cost. Yeah, so this is one of the drawback of it. The second drawback that we were talking about is the miniature workpieces cannot be worked. So small sized workpieces which are into mass production cannot be worked. But nevertheless, due to advancements in the burnishing technique, now a similar technique is developed wherein you can also work on the miniature workpieces. You can also improve the surface finish of the small sized components also. The another drawback that we were discussing is that thin walled components cannot be burnished because burnishing is basically a compression action or compressive force development or compressive stresses development activity and or a process. And since the thin walled components may not have that strength to take up those compressive loads, the component failure would be more dominant in that case. So the thin walled or thin surfaced components can be worked with metal burnishing. As I mentioned earlier also, that if the workpiece is having complex parts, complex surfaces which demand for a good surface finish, then the cost of tooling will further increase because special tools would need to be developed. In some cases, some surfaces might would be there which we cannot work to achieve that surface finish by a process of burnishing also. So that's the drawback. It is not suitable for ordinary finishing tasks, like where we will not normally recommend this operation to be carried out on the surfaces wherein a normal regular finish by conventional machining processes is acceptable enough. That is but obvious. No one would be paying something extra for unnecessary things. And then numerical assessment is required to verify the smoothness of the finish. Meaning, we'll take up two cases for the same workpiece. If a workpiece is turned by turning on a length, then to verify whether the component qualifies the requirements, we will simply measure its dimensions as specified on the drawing and verify that whether the actual measurements are within the tolerance that is specified on the drawings or not. We will keep it aside. But on the contrary, since burnishing as a process has its base to improve the surface finish, we will have to look onto the surface finish aspect of it, which we normally ignore in case of traditional machined components, unless and until it is specified on the drawing as a RA value. So, but if we are undergoing burnishing operation for some particular surface or a particular workpiece, then it is binding on us to verify the RA value by some sort of experimental measurements or numerical assessment for the measurements. So that's the additional thing which you need to perform here in this case of burnishing, apart from the conventional machining operations. Okay, so that's about the benefits and drawbacks of this. Let's take up a quick look at applications of it. So industrial applications of metal burnishing process includes the production of aerofoil components, health industry equipment materials or components of the health industry equipments, capillary tubes, needles of injectors, like in automobile industries, the nozzle injectors have needles. So these needles are basically used by the surface finish of these needles is improved by lapping process. But since lapping is cost consuming process and time consuming process, we can think of this ball burnishing operation there in that case. Food industry, since we require corrosion resistant components to have a quality of food to be processed into these industries, so burnishing can be one of the options in some of the components of these equipments. Turbine blades, since we need to have again a corrosion resistant turbine blade materials or turbine blades for their longer life, we can think of using burnishing techniques. Cutting tools, again, to have a greater fatigue life or greater component life of the tools, for a longer life usage of the tools, we can think of burnishing operation. And as I said earlier also, in roller burnishing, some hydraulic system equipments or components can be produced by burnishing techniques to have a longer life, because those components are always in contact with some lubricants, and lubricants might have some moisture which can cause corrosion and all those things. So to avoid those things, we can make use of metal burnishing. Now metal burnishing has all of these applications into industries, but these are the limited applications. It can be extended as and when the case may be. Based on that application, you can modify the tool that will be required to carry out the process. The process parameters need to be set accordingly, like the feed, the speed, the force of burnishing, all those things. Okay, let's move to the next slide. So this is the last slide, I guess, the applications of metal burnishing. Now, to my experience in my previous organizations, we used to carry out this metal burnishing operation on this sort of equipment. So visually you can see what sort of benefits or what sort of improvements it is carrying out there in the surfaces of the workpieces. So this is a normal traditional machined component, and this is ball burnished component. Again, this is normal machined component after casting. This is ball burnished component. You can see the surface finish visually. We have even the comparative chart mentioned over here. The RA value earlier, before burnishing, it was 1.075 microns. After burnishing, it came out to be 0.45 or 0.44 microns. And again, hardness in earlier case was 110 to 150, but after burnishing it improved to be 138 and 141. Now this hardness we are talking about is always a surface hardness and never a hardness of the material as a whole or at the core of the material. It is always at the surface, since cold burnishing is basically a surface treatment or surface finish operation. You can also go and visit this link to see the newly developed vibratory ball burnishing. This is the picture that dictates you the vibratory ball burnishing process, wherein a bucket or tub of hardened steel balls is given some vibration assistance to have the impact of those steel balls onto this workpiece, and some sort of coolant is used, the white colored coolant that you can see. So you can quickly go to YouTube and you can see ample of vibratory ball burnishing process videos there onto it to understand how vibratory ball burnishing process is there. So thank you everyone from my side about this. That's it from my side about this ball burnishing technique. So thank you everyone for your kind attention and patient listening to the process and this session.
Appreciate our efforts by subscribing to our channel. Thank you.